We're standing a couple of miles away from where the water main broke. This street is now a river. It rages through Cranston, Rhode Island. Many homes are without power. The people who live there evacuate. The water main that burst was installed in the late 1920s. That's considered old for a water main, but officials still aren't sure why it gave way.
Fortunately, disasters like this are rare, but they remind us how much our economy, our lifestyle, even our survival depend on the continuing good performance of networks of pipe buried below our streets. Water mains are the arteries serving our cities, sewers the veins that take away the waste. Culverts and storm drains carry streams and runoff around and through our cities and highways. Like good health, we normally take these services for granted, and rightly. Engineering science now allows us to design and construct efficient, durable underground pipelines with the same precision as we can build above-ground structures. But there is one big difference. An above-ground structure is a structure by itself and is designed to carry all the loads imposed. Most buried pipe rely in some way on interaction with the surrounding soil to carry loads. Virtually all buried pipe depend on proper soil support and therefore proper installation to provide good structural performance. This video is an introduction to pipe and soil interaction. It shows some of the assumptions that designers make about external loads on buried pipe and how installers must construct the system as designed to assure proper performance. The accompanying resource book expands some of these topics and directs you to further sources of information. Use the video and book together. First, we must distinguish between pressure pipe and non-pressure pipe. This pipe carries treated water. It is kept full and under pressure. A sanitary sewer or storm drain, on the other hand, is not usually pressurized and is seldom full. We also distinguish between types of pipe according to the way they interact with the surrounding soil, between rigid and flexible pipe. Rigid pipe do not deform significantly. They carry loads primarily through their inherent strength. When a rigid pipe is overloaded, it cracks. Various forms of concrete pipe, clay, and asbestos cement pipe are considered to be rigid pipe. Concrete pipe reinforced with steel to carry tensile loads are used for low pressure and non-pressure applications. Pre-stressed concrete cylinder pipe are used for pressure applications. The concrete cores are wrapped with pre-stressing wire under high tensile stress and coated with cement slurry and Portland cement mortar. Non-reinforced concrete and clay pipe are used for non-pressure applications. Flexible pipe perform by pushing outward against the soil at the sides of the pipe, using the soil stiffness to help carry loads. Larger diameters of bar-wrapped steel cylinder concrete pipe are considered as flexible pipe and are used for pressure applications. Circular smooth wall steel pipe are often used for long pressurized transmission lines. Various protective coatings and liners can be applied. Corrugated metal pipe, made of steel or aluminum, are used for gravity sewers and culverts. Galvanizing is the most common form of corrosion protection, but aluminum, asphalt, and polymer coatings are also used. Arch or elliptical shapes may be specified to meet particular site or flow conditions. Ductile iron pipe are centrifugally cast and then furnace annealed to provide the required properties. They are used for non-pressure and pressure applications. Ductile iron pipe are generally furnished with an asphaltic exterior coating and cement mortar linings. Polyethylene encasement can be used in aggressive environments. Bonded coatings can also be applied. Thermoplastic pipe, such as PVC and PE, can be of the solid wall type or structural profile wall, with a smooth interior surface to reduce friction and increase flow. Solid wall pipe are used for pressure applications, while profile wall and corrugated PVC and PE are used for gravity storm sewer and drainage systems. Thermoplastic pipe do not require coatings for corrosion protection. Glass fiber reinforced plastic, often called simply GRP or fiberglass pipe, are also used for pressure and non-pressure applications. Some fiberglass pipes are wound over an internal mandrel with continuous fibers, known as filament wound, chopped fibers, or both. This pipe, however, is centrifugally cast in an external mold and then cured. But this is not just a story about pipe. It is about buried pipe. So we must evaluate the soil environment in which we will construct our pipelines. Many aspects of pipeline design are site-specific. Once the right-of-way has been established, the engineer must investigate the site and local environmental conditions. These might include land contours, which would affect pipe alignment, areas of rock which could damage the pipe, unstable soils, water table level and fluctuation, the presence of other buried services, voids caused by earlier excavations, and any seismic activity. Research of past, present, and planned use of the land may indicate contaminants in the soil that might affect pipe durability. A simple resistivity test will reveal the presence of chloride or acid concentrations. Investigations may be needed to identify the presence of stray electric current or contamination from petrochemicals or solvents. The engineer must also establish whether any extraordinary live loads may affect the pipeline. These and other environmental issues will influence the choice of pipe and the design and construction of the pipe soil system.
In a pipe soil system, the most important properties of the soil are strength and stiffness. Soil strength and soil stiffness depend on soil type and soil density. Several classification systems are used to identify soil types. For simplicity, we will focus here on the Unified Soil Classification System, or USCS. Exploration logs of the soil along the pipeline alignment and any imported soils for pipe bedding are typically described in the plans and specifications using the two-letter symbols of the USCS. The first letter represents one of the four basic soil classifications. G is for gravel, S is for sand, C is for clay, and M for silt. The second letter of the symbol describes the particle size distribution or the plasticity characteristics of the soil. These systems are various expressions of three basic soil types: clean, cohesionless gravels and sands, clays and silts, mixtures of gravel and sand with clays and silts. Clean, cohesionless gravels and sands provide the best pipe support, especially when compacted. Clean gravels and sands are cohesionless, which means the particles do not stick together when dry. Clays and silts provide the least support for pipe, especially when they're not compacted. Clay forms hard clods when dry, and it's soft and sticky when wet. Silts are non-plastic or have low plasticity. Lumps of silt can be broken easily and feel like flour. Clays and silts are difficult to compact when too wet or too dry, and are often troublesome to work with. Natural mixtures of gravel, sand, clay, or silt from the trench excavation can often provide fair to very good pipe support, depending on the amount of sand and gravel, and be more economical than importing washed, processed gravel.
Density is the other key property of soils. Soil strength and stiffness increase with density. This is why careful soil compaction is a critical stage of installation. We'll see more of this later. Soil density is mass per unit volume, pounds per cubic foot in English units, or kilograms per cubic meter. Soil density is usually reported as a percentage of a density obtained in a laboratory test called the Proctor test. The result might be stated as 90% standard Proctor, for example. The type of soil and the degree of compaction should be specified as part of the design process. In the next section, we see how pipe and soil interact to form a pipe soil system. First, trenches must be excavated so that the sidewalls remain stable throughout construction. A movable trench box may be needed to provide a safe working area by preventing the sidewalls from caving in. The box has to be moved with care to avoid damaging the pipe or disturbing the compacted soil. Trenches should be left open for the least possible time. Exposed trenches may destabilize, flood, freeze, or present a safety hazard. It is therefore good practice to excavate just ahead of installation. Before we go any further, let us define the soil zones that can go into the construction of a pipe soil system. First, a foundation layer. This is needed only if the trench bottom is unstable or unsuitable. The bedding on which the pipe is placed. Filling and compacting the soil in the haunch area is critical for good pipe support and is often done by hand methods. The embedment, the material placed between the pipe and the trench walls that helps the pipe carry the backfill load, and then the trench backfill. We will consider some of the significant issues during the placement of each of these zones around the pipe. If the native soil is to form the trench foundation, it must provide stable, uniform support for the pipe. Organic material, or soft or low-density soil along the line, can cause unequal settlement. Very soft, wet soils can be replaced or reinforced by working in drier or stronger material and compacting well. Geotextiles or geogrids are sometimes used to reinforce quick or unstable soils, or to separate bedding and backfill from native soils. Transition zones are where the foundation changes from rock to compressible soil, or where the pipe enters buildings or manholes. These zones are likely to cause differential settlement, which may damage the pipe or open up joints. The transition point should be smoothed and shaped to make the change gradual. Pipe will accommodate ground settlement better if short sections of gasketed joint pipe capable of deflection are installed across the transition area. For all pipe, the trench dimensions depend on site conditions, the soil encountered, the type of pipe, and its size and shape. For rigid pipe, the trench should only be as wide as necessary for installation and backfill of the pipe. Here, a 96-inch ladder trencher cuts the trench for a 60-inch concrete cylinder pipe. Afterwards, specially designed compacting wheels allow a narrow trench with a clearance of only about 18 inches either side of the pipe. Where conventional equipment is used, greater clearance for working is often needed. The side support for flexible pipe comes from the combined stiffness of the trench wall soil and the embedment soil. If the trench wall material is stronger than the embedment soil, minimum space is needed on either side of the spring line. But if the trench walls are soft and weak, a greater width of compacted embedment or a stronger embedment soil, such as flowable fill, may be needed to resist the pipe's deflection. Bedding supports the pipe, distributes the load on the bottom, and should maintain the grade for gravity lines. The bedding thickness depends on pipe type and diameter. In the past, bedding was compacted, but now more and more organizations are recommending that the bedding be placed loose for a few inches so that it cradles the pipe. The particle size of the bedding is important. Large particles can cause a point load on the pipe and can damage coatings. In high groundwater areas, clean, free-draining gravel can serve as a drain. If the gravel exceeds the allowable particle size, it must be placed below the bedding itself. This means over-excavating the trench bottom and placing a stable foundation layer. Pipes should be checked for damage and cleaned of debris and then handled with care. Throwing or rolling the pipe into the trench can disturb the bedding and damage the pipe or its protective coating. The flexibility and impact resistance of plastic pipe reduces as the temperature lowers. Some types of dielectrically coated steel pipe also need to be treated with care in higher or lower temperatures. Most heavier pipe is best handled with slings of the right load capacity. Larger lightweight pipe, like fiberglass, is also handled in this way, though methods may vary around the world. Many types of joints are used, making some of them take skill and know-how. Most waterline projects require a laying plan showing the direction and location of all pipe components. If the direction of working is uphill, gravity will help with joining the pipe and drainage will be facilitated. Where the bell of a joint is larger than the pipe, a bell hole is recommended to accommodate the joint so that a stress point is not created. Here we see lubricated gaskets slipped into the spigot groove of concrete cylinder pipe. The pipe sections are then pushed or pulled together. The joint rings are protected by pouring grout into one side of a grout band until it flows around the pipe and up the other side of the band. This is the spigot end of a steel pressure pipe. Once the rubber gasket has been fitted and the tension equalized, the two pipe sections are pushed home. A copper wire is thermal welded to the two ends to ensure electrical continuity across the joint. The outside of the joint is then cleaned and coated. Unbalanced thrust can occur, particularly in pressure lines, where there are changes of alignment or cross-section at dead ends, connections, and valves. Preventing movement is to install thrust blocks of concrete behind and around the pipe. Restrained joints of sufficient length at these locations can help resist this movement. Steel coupling bands made for corrugated steel pipe can be corrugated and bolted around the two pipe ends to give an integral structure. Some are produced with two annular corrugations and a flat surface in between. For this joint, lubricated O-ring gaskets are slipped over the ends of each pipe. The coupling band is then wrapped around the pipe ends and secured with rods and lugs or other connectors. The gasketed bell end of this PVC pipe faces the direction of laying. The bell end is lubricated and the joint is then pulled together with the help of a come-along. This profile wall PVC sewer line can be cut to the required length and the gasket placed between the corrugations. The gasketed spigot end is lubricated and slid into the lubricated bell up to the stop mark. Joining methods for corrugated PE pipe include bell and spigot joints, coupling bands, and wire ties. Lengths of solid wall PE pipe are usually trimmed and butt fusion joined on site. Push-on joints are also used for ductile iron pipe. Variously configured gaskets can be placed in the socket restraining groove of the bell. Gasketed bell and spigot joints are flexible enough to allow longitudinal deflection of the pipeline. Ball and socket joints can provide a flexibility up to 15 degrees per joint. These can be useful for locations with changes of grade or alignment, subaqueous crossings, and in seismic areas. Some fiberglass pipes have push-on joints, and some have mechanical locks, which require only a lubricant in the field. For others, adhesive is applied to both ends, which bond together. Placing and compacting the embedment soil in accordance with specifications is the most important step. The type of embedment soil and the degree of compaction should be specified in the design. Embedment soil should be spread equally on both sides of the pipe and compacted to be dense and stable. The difficult part is here, in the haunch area. The soil needs to be placed and compacted with particular care if it is to support the pipe properly. The degree of compaction can be measured with an in situ density test suitable for the soil type, and the result compared to a laboratory maximum density. The method of compaction is often determined by the type of soil being compacted. Smooth drum or pneumatic tired rollers compact the soil by pressure. Impact tampers can compact to 95% standard Proctor if the soil is placed in lifts of suitable thickness for the soil type and compactive methods used. Sheepsfoot rollers knead clay soils, breaking up earth clods. The surface of each lift is left undisturbed, but gets compacted when the next lift is rolled. In this way, lifts are intermixed and bonded. Water may be added to assist densification. Vibration works best on sands and gravels. Vibratory rollers or plates shake soil particles, shifting them into a denser arrangement. Internal vibrators, such as concrete vibrators, combined with lots of water, can be used to compact soil layers up to 2 meters, about 6 feet thick. In high groundwater areas, it is also important that adjacent layers of different soil types are compatible. Fines in the bedding and embedment may migrate into the foundation soils below. Fines in the trench walls may also migrate laterally into the soil layers in the trench. To prevent this migration, a geotextile filter can be placed between soil layers or between the embedment and the trench walls. Soil excavated from the trench is used for backfill where possible. The economic advantages are obvious, but debris, large rocks, or organic material will need to be removed. However, soil types may be specified for 2 cushion zones nearest the pipe. Here, the maximum particle size will be limited. A minimum cover of fill should be specified to protect pipe from the effects of heavy trucks and construction equipment. Where pipes will be located below pavements, the soil should be compacted to the top of the trench to prevent settlement. Sometimes flowable fill is used in place of compacted soil. Flowable fill is a mixture of soil, water, and cement, and sometimes fly ash or additives. In pipeline construction, it can be used as the embedment, the backfill, or both. For both rigid and flexible pipe, flowable fill is placed to the same level as for compacted soil. Care is needed to prevent flotation or misalignment of the pipe. Once hardened, flowable fill provides structural support to the pipe, or in narrow trenches, transfers the load to the trench walls. It can be placed up to the top of the trench. Unlike poorly compacted soil, the hardened material will not settle. Flowable fill can have advantages in urban or residential areas where installation and repairs must be done quickly and suitable backfill could be a problem. Manufacturers check the materials they receive and test pipe throughout production. Testing assures conformance to relevant national and international standards and also compliance with product and contract specifications. Meticulous inspection is essential during an entire installation. Pipe size and class must be checked against the laying diagram or specification drawings. Pipe should be inspected for any damage incurred during transportation. Pipe that are lined or coated have to be checked for possible damage and any cracks evaluated. Throughout the project, it's important to follow procedures for the safe handling and storage of pipe, gaskets, and fittings. Pipe and joints must be inspected, the placement of the backfill monitored, and compaction levels checked at every stage of construction. Once installed, the pipe must be inspected and tested before the line is accepted. First, the interior may need cleaning to remove dirt and debris. The pipe can then be inspected with a lamp, video camera, or go/no-go mandrel for any local excess deformation or deflection. Larger pipes should be monitored for air quality before any personnel enter for direct inspection. Then, of course, pipe and joints must be tested for leaks. Pressure lines can be tested by pressurizing water at operating levels or greater. Double gasket or testable joints are available for some pressure pipe. Air can be pumped between the two gaskets to test them for water tightness as soon as they are installed. Gravity systems are tested by using low-pressure air, low-pressure water, vacuum, or by measuring the flow of groundwater into the pipe. These and other tests assure the quality of the pipe soil system, which the designer designs and the contractor builds. Good pipe design and good pipe installation depend on each other. Designers should design what they know can be built in the field. Contractors should appreciate that the pipe soil system was designed and strive to create that system. Pipelines that are properly designed, constructed, and installed will ensure long-lasting performance for many generations.